Good morning, everyone. Welcome to today's webinar. Before we begin, just a few housekeeping notes. You'll see the presented slide. If you could just please keep your microphones muted during the presentation. Just before we continue, can everyone hear me? Just a show of hands, please. Thank you. All right, so housekeeping notes, please keep your microphones muted during the presentation. You are welcome to post your questions in the chat box. And we will be having a dedicated Q&A session at the end of the presentation. We will also be sharing today's slides with all the attendees, and you'll also get an opportunity to get a certificate of attendance. This will present a slide towards the end of the presentation where you can scan a QR code and access your certificate of attendance. All right, it is once again a pleasure to welcome you to today's webinar hosted by the Engineering College of Science and Technology. Thank you for joining us for the second session in our Power Systems series. In our previous webinar, we explored the fundamentals of power systems, where we unpacked the core principles of generation, transmission, distribution, load flow, and systems stability. We examined how conventional power systems are structured and why stability, reliability, and efficiency are so critical in electrical engineering practice. Today, we're building directly from that foundation. So today we'll be exploring the integration of renewables into the power systems. As the global energy landscape shifts towards cleaner and more sustainable energy sources, power systems are evolving. The integration of renewable energy into existing grids includes new dynamics, technical considerations, and operational challenges. So understanding these changes requires a solid grip on the fundamentals, which is why our previous session remains an important reference point. If you're unable to attend the first webinar, we encourage you to please access it through our YouTube channel, as we've provided valuable background that complements today's session. So today's session will explore how renewable energy sources such as solar and wind are integrated into power sources. This is a critical area of knowledge for modern electrical engineering professions, as the future of power systems is increasingly renewable, decentralized, and intelligent. My name is Busisiwe Mateo, and I'm going to be your host again for today's session. It is once again my pleasure to introduce you to our presenter today, is our lecturer, Mr. Samkelo Nene, who will guide you through these technical critical discussions. Samkelo is a registered Candidate Engineering Technologist with Candidate Engineering Technologist with ECSA. He also holds a BEng Tech honors in electrical power engineering. His academic journey has been marked by excellence in leadership, earning him recognition through his induction into the Golden Key International Honor Society. He has further strengthened his expertise through his involvement in sustainable energy initiatives with the South African National Energy Development Institute, contributing to practical solutions with the evolving energy sector. So we are proud to have him on our as one of our valued members of the academic team here at the Engineering College of Science and Technology, where he continues to shape and inspire future engineers. Samkelo, over to you.
Good day, everyone. Am I audible?
Yes, we can hear you.
Can I take over the slides? Take control, rather.
Yes, please.
Thank you. So good day, everyone, once again. Today we'll continue from our last webinar, where we covered fundamentals of power systems, basically looking at the entire power system from generation of electricity to transmission to distribution up until the end user. So today, now we are considering the integration of renewable in our grids, which is one of the topics, okay, of this day. Uh, all over the world, we are aware of the likes of climate change, um, energy access. We want to reach energy access, global energy access by uh, 2030, net zeros, and so forth. So this is our list of contents for what we cover today. The introduction, which will sort of touch on the previous webinar, and then we'll move on to sort of like setting the context as to how this all started. And then we will look at technical challenges, operational implications, enabling technologies and solutions, and also some case studies. And then we will end our session. So let me move the slide. So last time uh, we covered fundamentals of power systems. In a nutshell, basically, this graph sums everything that we covered from the power generation, where synchronous generators produce electricity. Obviously, there's a fuel that is employed in the process, whether you're using fossil fuels, coal, or the renewables, it's solar or wind. And thereafter, then this is then stepped up as we see using transformers to higher voltage, which is transferred or transmitted over longer distances to avoid losses. And then it's distributed. Then there are different, obviously, to different consumers. There's industrial, there's commercial, then there is residential, that being our houses. We also learned some of the core concepts. We also explored the history of DC versus AC and how that most of our power today is transmitted or transferred using AC uh, AC systems, in particular three-phase system being efficient and also transfers constant power. We also even talked about in terms of designing um, of networks. Basically, if we were to look at a grid or a microgrid, we will then have a simplified representation of the network using single line wiring diagram to make it easier to analyze and design um, these networks. And we also look at some key analysis as well, uh, starting from the load flow analysis, which is done to determine the voltages, the currents and the power flows in a steady state condition, for example. And we then also touched on power system stability. I just hope the slides are clear on your end. Uh, just give me a sign if they are clear, the graphs. But they are clear. Thank you, Danny. Thank you, Lisa. Maybe it's my eyes. Maybe I have to go see an op an opto. So we also looked at the power system stability as well. Uh, Starting from the rotor angle stability, which ensures synchronism between generators after after the disturbances. So as we know, in South Africa or South Africa, Africa, and also Europe, our sort of like standard frequency is 50 hertz. So basically all the equipment are synchronized to this 50 hertz. And obviously if you look at the North America, so Basria, you cannot see the slides. Is anyone else gonna see the slides? I just tried to that chat. I see Basrai said he cannot see the slides. Okay, I'm not sure what's happening with Basrai, but others they can see. Okay, so Uh, Maybe you could perhaps leave and then join again. Maybe it's a network issue. So, in terms of frequency again, um, it's 50 hertz. So all the equipment is synchronized. So it's a quite a long history. Uh, I'm telling you, it's very interesting if you could go read about it as to how they came with 50 hertz for uh, uh, the Europe, Middle East, Africa, and then 60 hertz to America. I think it's same as like how the North in terms of like America, they still using imperial system, and we are using the standard or the SI units rather. It's sort of like those things kind of, but yeah. So in essence, basically, look at the south and the east, and so the north basically, that's being the UK. We are all using 50 hertz. So all the equipment in the system are synchronized to 50 hertz. So basically, rotor angle stability ensures that there's still this synchronism even after there's been disturbances. And then frequency stability, obviously, um, in terms of like mismatches when it comes to generation and load, if there happens to be there's more demand than the supply, or there's more supply than the demand, then there'll be deviations in the frequency. So frequency stability is all about that, ensuring that the load meets the demand, which is very an interesting uh, role, especially eh, in this context that we're going to unpack today of renewable energy. Then the voltage stability as well, it's about ensuring steady voltage at the buses and so forth to avoid a voltage collapse. We also touched on protection in terms of faults, circuit breakers, how switch gears, and all those protect our system. Uh, yeah, so I don't want to dwell much on this, sort of like a recap. And these ways is essential components that we visited. Uh, the yellow one being the synchronous generator, and then below are the transformers I've explained, which simply then switches the voltage, or rather step up or down, and then the transmission line we transmit, and then the last part sort of speaks of the switch gears. Um, and then we see on the left the capacitor banks. We did touch on that. The importance of reactive power, especially when we want to if there's over voltage, obviously we then deal with reactors. But with the capacitor banks, if there's under voltage, then we supply or we inject the reactive power to sort of balances the voltage or to bring it up again. So the importance of renewable energy integration in today's energy transition. It's a long story. Um, Probably started around the 2000, 2001 and all those when the talks of climate change began, you know, and also meeting or having that average temperature of 1.5 degrees Celsius, basically. Uh, there are a lot of frameworks, there are a lot of organizations, governments, uh, diplomats working towards this goal. So it's energy transition and also climate change. So we can use this basically interchangeably, but however, climate change is sort of part of energy transition, because when you speak of energy transition, it's more than that. We also speak about things like energy security, economic security, environmental security. So basically, what we sort of or what these frameworks, governments, they're committing towards basically is for countries, for regions to have dependence when it comes to energy security. Um, when the amazing thing about the renewable energies is that as long as you have the sun and wind, wherever you are in the world, you can generate, right? Obviously, there are parts of the world where they are favorable when it comes to the solar radiation and so forth. But again, if you look at what happened during the weekend in the Middle East, uh, and things will, again, we're gonna rise the prices, the fuels, because of the geopolitical tensions, basically. So geopolitical tension, they tend to then threaten uh, national security in terms of like exporting or importing some of the fuels that we use as part of our energy sector. So renewables basically is that, or rather is sort of encouraged because it sort of promotes energy independency. When it comes to economic security, it stimulates innovation, job creation, and the environmental part of it, which is then, even though it's sort of also a big debate, we say that it generates electricity without emitting greenhouse gas emission. But one as well can argue, and that's how are they manufactured as well? Because uh, we use what? We use fossil fuels to manufacture them, right? Because to manufacture a renewable components and all those things, you will need an intensive energy source. So that's also another debate for another day. So hence we have this sort of energy trilemma where we trying to balance energy security with economic security and also environment. And sometimes, and well, most of the times you have two, you cover two, and the other one is not covered. So it becomes sort of like a trilemma, which our governments and all that, our United Nations Framework Convention on Climate Change, they are trying to address. And one of the reason really, I think we'll see the stats here by the International Energy Agency, where we see growth in the project of global wind and utility scale solar power plant projects, basically. Obviously, this is driven by the global sort of target to triple renewable energy share in our global energy. So I think it was the conference of the parties, that the 28th one that was in UAE, where countries under the United Nations Framework Convention on Climate Change, they came to commit to tripling renewables to 11.2 terawatt. And if you look at this project, it's like we're halfway through. So basically, we are yet to see more of these projects and also penetration of renewable. That's why we then have to then uh, visit this. So if we look at the characteristics of the renewable generation, it's variable, it's intermittent, it's unlike your typical generation, your conventional generation, where it's dispatchable, where it's flexible. So obviously the power plants, they vary. We have the peak plants, which you can just ramp up and ramp down, easily, which are your natural gas and so forth. Speaking of natural gas, South Africa, majority, if not all of our gas, we we get it from Mozambique, right? So already that is not good if you think of geopolitical. If something happens one day, uh, we won't be able to get that gas. Even though we have heard of developments about shale gas and all that, we haven't really, uh, I wouldn't say gotten a solution, but um, our gas is exported anyway. So until then, the development of shale gas that they're working on uh, becomes, maybe produce something fruitful. Until then, we're dependent on the export of gas. So I was speaking about peak plants. So the peak plants, you can call them anytime, like you can bring them online like easily. Then we have the base plants, which are your coal. They are dispatchable. Obviously, you'll have to plan. when to bring them online. Um, Obviously, they don't ramp down easily as your peak plants, your diesel and your this thing, yeah, sorry, your gas. So with renewable, you can't do that. You can't just bring them online and all that. So it's based on the availability of the solar irradiation of the sun and the wind. So whenever we have that, we have to then maximize. So whether we have to store that using battery energy storage, and we'll touch on that anyway, or hydro pump storage. So when you speak of variability, if you look at a typical voltage sign, if we look at voltage rather, voltage the voltage wave sine wave, uh voltage waveform rather, it's sine, right? We use sine for example to represent it. One could also argue with cos, but if you look at the representation of the peaks, there's consistence, right? Even though obviously it's a changing current or changing voltage being AC, but with renewable, there's variability. It just ramps up and then something happens, then it comes back again. You can like it's not consistent basically. Hence, it's variable, and also the uncertainty as well. Like here, you look at the forecasted. This was forecasted using historical data that at this time, this is how much it will produce. But look at the actual what it did produce. It's above. Sometimes it can be even below what was forecasted. So it also brings that element of uncertainty. So it's not easy to sort of manage power flows, especially coming from the renewable. So it's sort of like an interesting study. As I've said, all over the world, people are trying to sort of find ways to integrate renewables into the grids. So these are some of the examples that we see here. This is a solar installation before I move on, and we can see its variability, how it changes, and also its uncertainty as well. We can see even here the frequency. This is the wind turbine. So again, I did on this the comparison between conventional synchronous generation versus the renewables. Again, just to add on what I did explain, the the conventional synchronous generation obviously is that it is directly uh, coupled using the rotating machines. So these rotating machines basically they sort of provide inertia. Inertia is, I'm sorry, when I look at the second screen, I'm looking at the presentation because it's bigger, so I'm able to see here. So basically, when these rotating machines, basically what they provide is inertia. Inertia is sort of like resistant to change, basically. As if we were to look at the solar, at the rather renewable generation, they are connected or basically inverter or power electronics are used are sort of like in between when it comes to them interfacing with the grid as compared to the generators where they are directly coupled. So obviously power electronics does not have natural inertia as the synchronous generators because they are static, but we will also review that. So some of the challenges then, which is the main one basically, which is power fluctuation, as we saw, the invariability and also the uncertainty as well. So then this leads to power fluctuation, and then it becomes a problem then to balance the load. Again, because you cannot just dispatch renewables. You have to work with what you have at the time. So if you have excess, then you have to also find a way to store that excess. And then if you have a less, then you have to sort of find flexible generation to complement renewables. And this also have an impact in planning. It becomes difficult to plan ahead when you speak of long-term planning, because we saw that even on the first graph that sort of um, you can sort of forecast, but it won't turn out that way most of the time. So it becomes difficult to plan. Whereas with coal, you know that coal power plant has that capacity and can produce so much power. You can plan that ahead. Same with also the flexible generation, the one that you can ramp up and down and now and then. You can plan that because the system, you know, is sort of like, you know, like we call them base loads and flexible generation. You can dispatch them easily. With renewables, you just have to work with what you have. So it makes it difficult. And we see here again, we see the demand in the red, that demand. So this is across this time. This is a day basically. It's a day. We see 20, that's 10 to 24. It's across the day. So we see that from here in the morning until like somewhere afternoon, the solar power is at its peak. Basically, it's getting the most solar radiation, hence it's generating so much power. But there isn't much demand, most likely because people are at work and all those things. But look at later, look at the demand, how it spikes. And later, there isn't much solar radiation falling on the solar panels. Hence, we have this sort of this we call it the dark effect, where there is so much during the day, so much power generation, but there is no demand. So then we have to ask ourselves, then what do we do with this demand? Because I mean, with this supply, there's so much power. Yet later, if you look at the generation, it just drops. The demand then spikes. So then we have to find a way to match these together. So it becomes an interesting which technologies then we use to do so, and we'll unpack this in the next couple of slides. And also this the graph below sort of represent the grid frequency, where we see deviation of the grids uh, when it is renewables and has no renewables. Okay, so we speak of the primary frequency response and also the fast frequency response, and we will touch on that as well. So these are some of the challenges that we'll be unpacking today. And also inertia, as I've mentioned, is also uh, when you speak of frequency, we cannot leave inertia behind because if there is less inertia, example, when we talk of ESCOM decommissioning power plants and all those things, because majority so far of our power plants are in here in SA, for those who are in SA, uh, over 80% of our generation of electricity comes from power plants. So those are synchronous generators. So if we're decommissioning them, it means that we will have less inertia in our system. And there are a lot of case studies, some of which we will cover here, but all over the world, we've seen grids with less inertia, how fast the frequency deviates and leads to grid collapsing. So reduced inertia is one of those challenges also. Uh, that electrical engineers, system operators, they try to address, especially in these transitions. Again, this is the same graph speaking of the fast frequency response and the primary frequency response. So basically, they're both response uh, uh, put in place when the frequency deviates from the standard, which is our 50 hertz here. So obviously, there will be a limit plus minus 2%. Uh, the fast frequency response, or starting with the primary, perhaps the primary frequency response. So this one basically it sort of like generator based. Oh, so we here the speed governors are employed then to sort of um in terms of like the generator output, to make it proportional to the frequency change, basically. As we did explain that the generator, the rotation, or the inertia that the synchronous generators then produces this resistance to deviation. So that's sort of like the primary frequency response, where the generators are providing this resistance, this inertia to the frequency deviation. Whereas with the fast frequency response, then okay, the primary it's sort of like within seconds, and then the fast frequency response, that's like milliseconds. So with that one, so basically we employ your inverter-based resources like batteries and also distributed energy resources. So basically this one is about injecting power if there is more demand than the supply, or if there is less demand and more supply, we then absorb that power. So basically it becomes that game of matching the generation with the demand. You can't say because there's so much generation, it's so good. It's not good for the system. Like at all time, there has to be a match between the generation and the supply for the system to be stable. Because obviously high generation will lead to higher frequency, and that can have mechanical or that can lead to mechanical damages on the generators equipment at the generation side of the power system. And also you can't say it's okay, we can work with less load. That will bring the frequency down. And obviously it will burden the grid because there'll be more demand uh to on the grid rather. So another one is voltage stability issues. So if we look at generators they use excitation systems basically, which they supply DC currents to the field windings, which then leads to um, the magnetic field that help produce the electricity basically. So that's one of the function of the excitation system. Also, this excitation system helps with also providing the reactive power. So basically, if we take away these synchronous generators, we are not just messing with the inertia, but we are also uh, messing with the voltage stability. Uh, One could argue then, but we can use reactive power management. We can induce reactive power. You know, However, uh, the grid, okay, as we explained, the synchronous generators they tend to respond quickly. With the inverter-based resources, it's all based on coordination. So if the coordination is poor, then that will lead to grid collapsing due to voltage stability issue. So this is sort of uh, basically the reactive power margin. Basically, this here being the nose, the maximum power that can be injected to that network before it collapses. Basically, this graph depicts that. So reactive power is important because um, when you speak of power or apparent power, we would have the actual power. We say it's the power that does the work. Um, we also have the reactive power, which is very important when it comes to voltage. And we did cover this on the previous webinar that we need reactive power. So it's either we absorb or we inject. So we inject when there is when the voltage falls below its sort of acceptable limit, and then uh, we inject in that scenario. But when the voltage then is above its acceptable limit, we then absorb it. So this is one of the examples in Europe 2019, where there was a drop in frequency. So these numbers, these are some of the events that happened. So there was a lot of speculation around this. You know, if you remember, Some of them was that the data was incorrect. Basically, the data that was going to the control centers. And also, if you look at around eight, at the first one, this one where one of the coal fired power plants in Spain, one of its units or the boiler went off, uh, obviously taking off about 152 megawatts or so. And then the second one being a nuclear power plant in France, which also went offline. Uh, so basically, all these units and these power plants going offline, it's reducing the generation that goes to the to the grid. And once there's less generation compared to the demand, then the frequency then drops. As we see here, this is what eventually happens. It drops. So one of the practices or one of the sort of like solution that they used, especially the French transmission company or operator. Their operator was then to call their industrial um, consumers, which they call them industrial demand demand side consumers, to ask them to reduce their consumption. By doing that, obviously, then they reduce the overall demand of their grid. Uh, and one of the other ones that we can think of is load shedding. I know load shedding, we don't want to hear about it. It is also one of the techniques that we employ. If there is if there is uh, more demand on the grid than the generation, we then employ these interrupted, these planned interruption, basically, because there's a difference between a blackout and a load shedding. Blackout is not planned. However, load shedding is planned, basically to reduce it. It is employed to reduce the demand on the grid. So here it's reached to 49.8 from 50. So that's about 0.2 hertz. So that's 2%, plus minus 2%. So it's almost collapsed. This grid almost collapsed. The thing about frequency, when you look at the values, this 49.99, 49.98, it looks so insignificant, but it makes a lot of difference in the grid. It makes a lot of difference. So hence we have these grid codes, as I've mentioned, for frequency plus minus 2%. And another case study is the Australia, South Australia, where there was tornadoes. By the way, in SA, we have never had a national blackout. Um, we are yet to have one. Well, I hope we don't. But with the integration, with what the National Transmission Company is working on, we are integrating more renewables. Um, it's scary. It's scary. I'm just thinking of this now as I present here, that we don't really have experience in blackouts as compared to other countries. So I wonder what will happen. We are used to, we are experts when it comes to load shedding. That's we have, in that regard, we are experts, operating near the limit. But when it comes to black starts, we've never experienced one. So I wonder how that will turn out, since we don't have experience. Because if you look at this one, if we look at this case study or this example, because this happened. So two tornadoes sort of like, struck across South Australia, and as we see here, the tower of or the pylons rather, for the transmission line, it fell. There was lightning. I think they said there were about 80,000 lightning strikes. The transmission, the grid was damaged. The moment the grid is damaged, the moment their transmission lines, whether corridors or if you want to use conductors, once they are damaged or disconnected from the grid, already that grid is under strain because it's no longer operating in a normal condition. or the steady condition. So that alone already puts a strain on the grid. So, by the way, this was storm induced. So this was just nature. It was just nature, and even worse, with high wind now. Then now there's also high wind. So high wind it means high generation, more generation using the wind turbines and the wind power plants. So here's the grid. Its capacity is no longer normal, basically, since part of it is damaged. And then here's the high penetration of wind energy. Catastrophic. So, so basically what happened then, before we move to the next one, this grid collapsed. There was a blackout. There was a blackout, and obviously when there's a blackout, they do a black start where they sort of like bring back, sort of like bring back power and all of those things. It's interesting. I think the former executive or the former GM, when it comes to NTCSA, when it comes to the system operation, system like operate system operator, basically. If I remember, it's Miss Elizabeth Fick. I remember in one of her presentation with CSRR, she mentioned that if South Africa were to experience a black start, it will take us 14 days to recover. Imagine 14 days. I think that's one of the things, it's one of the reasons rather I was just wondering, because if you look at these scenarios, for example, with Australia, um, in 3 hours, some parts was restored, and then the other in the next 3 hours, which is about 6 hours, and then for the rest, it took about, you know, another day and a half to restore. But again, if you look at these places, basically, even like America, they've experienced blackout, they've experienced in blackout. And I think that's why with us, then it makes sense when ESCOM comes and says, uh, and announce that it will take us 14 days because we don't have that experience when it comes to blackout. The last or the blackout that we have had was the Natal blackout, which we did cover in the previous webinar, and also that Western Cape blackouts. But those are regional blackouts, not national, because the thing with regional, we can then sort of transfer power from the other regions to sort of supplement and assist. But if it's national, we got no power coming unless maybe you are in Europe, where if you look at their grids, like their grid is interconnected. Hence, that's why if Spain sort of like was it Spain when they were I think it was one of the last blackouts that happened in the Europe. I think it was Spain and also France, but however, France, they were able to disconnect from the grid the moment it started, to weaken. And also they have nuclear power plants, hence they have this base load to sort of, resist frequency deviation. So it becomes very interesting. So we see with this one high penetration of of wind energy, and also uh, the grid capacity also was just not normal due to the damage that was due to the storm. This led to a collapse of the grid. So basically, a grid can collapse in a matter of seconds, and I think that's like the scary part. And this example, or this case study, is what happened in California. So a lot has been happening in the US. I think of all the continents, US, North America, or we can say US as the country, but not North America in particular. There are a lot of examples in the past in the past years, basically, where there was sort of like a grid collapse due to renewables and all those things. With this one, it was due to heat waves. Um, so it was very hot. Temperatures, obviously, they were high and all those things. And when it gets hot, the first thing we want to do, we want to open our air conditioners. And when it's cold, we want to use our heating, our heating equipment or whatsoever. If you look at like at the global consumption, I think the last time I checked, one of the main contributors to demand or consumption is heating and cooling. It's heating and cooling. So here in this case study in California, it was hot, obviously. In fact, USA, obviously we see the Western America here, and in the first picture, basically, is what came out the day before this happened, the collapse of the grid happened. Basically, that the temperatures will be high, it will be hot, and all those things. And obviously, they are operators. So, unlike us, we have one national uh, system, sort of like national transmission company. That side, they have regional transmission operators, with their different states. So they operate differently. But for this now, California, they were aware of what was going to happen, obviously, uh, given that there will be high temperatures ahead. So by looking at this and also the stats that whenever it's hot, there tends to be a high demand due to the need of cooling and all those things. And uh, the demand was high that even the resolve couldn't meet, couldn't what was not enough to meet the demand of or due to this need for cooling. And in the second graph, there are two demands. So there is the actual demand and then there is the net demand. So the actual demand is sort of like the gross demand, the total demand. And then the net demand, the net demand is after you have taken out the behind the meter means of generation. So that's been your rooftop. So even those who were using their sort of like backup, even those backup couldn't meet the demand. And you see, these are sort of like both the demands basically. So the actual being the total, this is the demand after injecting or after using those behind the meter. So even after some people use their own sort of like generation, being rooftop, obviously, you wouldn't have a turbine on your yard, being rooftop solar panels. Even after they've used that, it's barely went down. It's still up there. So from 44 to about 42, that's about what? Two, 2,000 megawatts. It's a lot, but if you look at the previous demand in terms of change, it's not as much. And this was at night. So if you look at the one towards the corner, you look at the generation of the wind and the solar, you see the wind is blue there. It was just barely producing any electricity. Whereas with solar, we see that during the day, obviously it was producing as much as it could, but obviously towards the evening and night, it drops as we expect it to do. However, the demand stayed throughout the night. So basically, solar re the, the reliance in solar both sort of exposed the power fluctuation during the day and also at night as well. Uh, Solar obviously not a variable, even using or employing storages were not enough. As I've said, that the reserves were not enough to meet this demand. Hence, the grid then uh, collapsed again. And also, it took days to recover this grid, but it was faster than 14 days that we anticipated South Africans. So these are some of the examples, basically, of the grid collapses due to the high penetration uh, or integration rather, because the previous one it was the high penetration of wind. This one, it's more of like, well, both is integration of wind, but with this example, it's not a matter of high penetration, but it's a lack of then production or or mismatch of demand with the supply. So in the previous instance, high penetration of wind energy that leads to overall uh, high generation, high frequency, not good as well. Obviously, the generators will then trip. There'll be trips around the grid, which will lead it to sort of shut down. And then the second part, where there is more demand and less generation, which is the California part, the system just couldn't take it. Um, they also did sort of try to took the approach with what the France transmission operator did, to ask for industrial consumers to sort of reduce their power consumption. But there we saw that it helped because the grid sort of came back. But here, even after those requests, those uh, uh, it's emergency rolling blackout request. Even after those emergency rolling blackout requests, still the grid couldn't just take it, so it collapsed. So if we look at some of the operational implication, we need advanced forecasting and scheduling. Again, it's tricky. We talk of AI, we talk of large language models, agentic AI, and all those things. Um, we can employ these tools to sort of advance our forecasting and scheduling, but renewable, it remains intermittent and invariable. Hence, it's also important to start considering, well, we do know, but to keep in mind that we have to then complement renewable flexible generation. So yeah, the first one is being advanced forecasting and scheduling. Um, I know AI is sort of like hyped and all those things, but these are the things that we should start thinking about when it comes to forecasting and scheduling, to have as much data to train the models to sort of forecast as to how much will be produced and so forth. Because with the demand, we can sort of do that. There's a pattern when it comes to the demand, because the demand is us human beings, so we can sort of pick a pattern. But with renewable, it's just invariable. It's not consistent, so it becomes difficult then to forecast the generation as compared to what we're expecting in terms of the demand. And then also grid codes as well. Um, even so, the second part basically it shows a snippet of the operating range of the frequency. So this was taken from the grid code, especially for integrating renewable power plants. So by NERSA came up with this document basically in terms of limits, frequency, voltage, and also renewable curtailment over during over frequency. But we'll get to that just now. So grid codes are very important because they sort of give this information basically uh, in terms of like the voltage levels, the frequency levels, and the first graphs here again. Uh, but this is standard even on the normal grid. This is sort of like what we expect when it comes to our frequency to operate within this range um, of 49.9 hertz to 51.1 hertz. And then here it's the voltage again, the level of the voltage between 0.85 to, okay, I can see that in 5 minutes. I'll try to be quick. Between 0.5 to 1.1. So this is sort of like when you speak of the percentages, basically 85% to 1.1, even though uh, it's recommendable at least to be at least above 90%. But for this one, for this document of integrating renewable power plants, this is sort of like the condition. And then also speaking of power curtailment during overfrequency, as we see here, we have the power and then versus the frequency. So as I've said, when the frequency drops, or rather when the frequency increases, it is due because there is sort of like this overproduction of power. So we then need something to sort of cap it. So that's what power curtailment does, is to intentionally sort of reduce the generation or to cap it to make sure it meets the demands. So grid codes also cover the requirement for scenarios as these. And then the role of system operator, again, as I've said, is to balance the supply and the demand. So yeah, it's an interesting role, especially currently. It's an interesting role with, especially when you speak of integration of renewables. Then how then you then mesh the load with the supply, especially when the supply part of it is not consistent. And then coordination between transmission and distribution network to ensure efficiency, to be honest. Because if you look at most of the distributed energy resources, they are connected via the distribution network. So we have to sort of find a way, to have better coordination between transmission and distribution, because then distribution can help support transmission. Uh, because transmission, that's where we sort of, match the demand and the supply. So it's very important to better coordinate uh, transmission and distribution network. These are some of the these are some of the technologies that we mentioned. I did mention that if we look at hydro plants, um, they are good when it comes to backup. Also, um, the battery energy storages, they tend to respond faster. However, for short duration, when there is sort of frequency deviation, whereas with hydro is mature, it's large scale, so it can even be used for much longer duration to sort of stabilizes the system. There are obviously other forms of storage, which I won't touch now due to time. And then flexible generation, as I mentioned, we have the gas turbine, which can ramp up and down easily to sort of inject power if there is a decrease in power, to sort of bring the frequency again up to its standard. And hydro again can be used as a backup. And then on the next webinar, we will cover smart grid technologies, demand response, where we basically the demand. We shift the demand to meet the supply. Currently, what we do, we sort of add to the supply to meet the demand, but with demand response, we just sort of like shift the demand to meet the supply. It's the other way around. I see Busi, your mic is opened. I'm almost done. So we will cover this in the next webinar, but I wanted to put it as one of the enabling technologies. And then grid forming inverter, we won't watch this video now. So basically grid forming versus grid following. Currently our inverters are grid following. Basically, they just follow the frequency and the voltage. With grid forming inverters, whenever the voltage here, if you see this, whenever the grid voltage drops, then the current from the grid forming inverter sort of shoot up to sort of compensate or inject power, to bring it back up. This is an interesting simulation from MATLAB Simulink. You can find it there. And yeah, man, and this is our context. As I've explained, we're decommissioning, and we are bringing more renewables. And one of the plans that ESCOM has is to then deploy synchronous condensers, which will sort of provide inertia or natural inertia that we need to stabilize the grid. Because without the natural inertia, chances are the inverter-based or the injected or the synthetic inertia, if it's poorly coordinated, it will lead to grid collapses. So we can't afford that. Hence, we have some things in place such as condensers. Yeah. So that's all for today. I'll stop right here.
Thank you very much, Samkelo. I see we are over time, or we are just at the end of the presentation. I'm going to open for question and answers. If there's any, if you could just please just drop them in the chat, and then I'll just read them out loud for Samkelo to address. In the meantime, I'm going to display the certificate of attendance slide. If you can just please scan that QR code or just access the website that's provided there. Are there any questions that we can just address quickly, please? Okay, I am not getting any questions. I think you were very clear in your presentation, Samkelo. I think, yeah, everything was covered, even though we did just rush through the last slides. But again, the slides will be provided to the attendees, so you can just take your time and go through the slides on your own time. And we have got other upcoming events that you can also just to join. Just also our ECST program intake, we are offering the Bachelor of Engineering Technology in Electrical Engineering. We will be having intake in July with the start date of August. So if you are interested, or if this presentation has just sparked an interest, please just visit our website and apply. You can also just forward this information to any of your colleagues, students, and we've got upcoming webinars. We've got the virtual information session on the 18th of March, where you'll get more information about the college and the products that we offer. We have got the Advanced Power Systems Protection and Smart Grid Technologies webinar that's also coming up on the 18th of March, as well as the Energy Storage and Grid Flexibility in Modern Power Systems on the 1st of April. So please feel free to visit our website and register for these webinars. Thank you again. I'm still not seeing any questions, so I think we will just close. Thank you again, everyone, for attending this webinar. Thanks, Samkelo.
Thanks, everyone. Take care. Bye.